Hi, my name is Claire Elgard, and I'm going to be recording my Unit 4 case connections responses. So for the first one, I chose to do case 1. So a day-old baby girl presents to the doctor with symptoms including lethargy, hypothermia, and apnea. When blood work is done, it shows extremely elevated blood ammonia levels that continue to rise quickly. So the rise in blood ammonia levels is most likely due to a nitrogen transport deficiency that does not allow for the ammonium to be freed and go towards the urea cycle to be excreted. However, ammonia remains stuck in the liver and increases blood ammonia levels. The normal process of ammonia transfer within extrahepatic tissues, liver, and muscle includes glutamine synthetase, glutaminase, glutamate dehydrogenase, and transamination reactions. So ATP and glutamate will fix to ammonia in the peripheral tissues and go through glutamine synthetase to produce glutamine. This glutamine will then travel to the liver and utilize the glutaminase enzyme that frees the fixed ammonium to go towards the urea cycle and also produce glutamate. Then the glutamate dehydrogenase enzyme can produce alpha-ketoglutarate that feeds into both the TCA cycle and transamination that will occur in the muscle and the liver. So the transamination process is in part known as the alanine glucose cycle specifically here. Transamination requires pyridoxal phosphate as a cofactor and plays a large role in transferring nitrogen rather than freeing ammonia. Alanine within the muscle is an alpha amino acid that can be transaminated to the alpha keto acid pyruvate with the transfer of nitrogen and involvement of alpha ketoglutarate and glutamate. During a fasted state, alanine can be released from the muscle and transported to the liver to be transaminated to form pyruvate that will act as a substrate for gluconeogenesis. Further blood work shows an increase in urine orotic acid levels as well as the elevated ammonia levels. Other blood levels, including the citrulline, remained within the normal limit, but on the lower end of the spectrum. So these levels indicate a deficiency in the ornithine carbamoyl transferase enzyme. This enzyme typically functions to produce citrulline from the ornithine and carbamyl phosphate. The inability to produce the citrulline explains why it's on the lower end of the normal, and this also explains why there's an increased ammonia in the blood. This is not going to be a deficiency in the argininosuccinate synthetase because citrulline levels would be higher in this case, since this would be the last product produced prior to this deficiency, and there would be no accumulation of carbamyl phosphate or ornithine as well. Arginine, which is normally a non-essential amino acid, will become essential with this deficiency. So this deficiency causes the urea cycle to have difficulties forming its products fully. So this would affect the levels of fumarate and arginine that are going to be produced. So typically the body can make enough of its own arginine through the urea cycle, but with this deficiency, this amino acid will need to be supplemented within the diet. So that is the end to the answers to the first case that I chose, and the second case that I chose was case number 2. So within this case, scenario 1, there is most likely a deficiency in the dehydrogenase enzyme. Specifically for branched chain amino acids, this is called branched chain alpha keto acid dehydrogenase complex. So this deficiency will lead to a decrease in the metabolism of branched chain amino acids such as leucine, valine, and isoleucine to produce substrates for the TCA cycle. Branched chain amino acids are already essential amino acids since they are primarily degraded by the body to produce energy. A disease that can stem from branched chain amino acid deficiency is something like maple syrup urine disease. So this is when accumulation of branched chain amino acids become toxic due to intake of essential branched chain amino acids and being unable to be degraded through the metabolism process. This can have presentation early in life and show symptoms such as lethargy and seizures. Treatment includes dietary changes that will allow for the intake of other essential amino acids while avoiding foods that are high in leucine, valine, and isoleucine, so those branched chain amino acids. In scenario 2, there is most likely a deficiency. In scenario 2, there is most likely a deficiency in the homogentisate oxidase enzyme. So this impacts the metabolism of tyrosine and will lead to increased levels of homogentisate. So this is known as Alkaptonuria due to the production of alkapton. Ochronosis is the accumulation of homogentistic acid in connective tissues, and it is what is causing the joint pain that the patient is experiencing in this scenario. There are no amino acids that are becoming essential as a result of this deficiency. Unfortunately, treatment by megadosing vitamin C has been tried, but clinically it has not shown much success. And there are no other supplements that can be used as treatment. It is mostly just symptomatic control. In scenario 3, there is most likely a deficiency in the phenylalanine hydroxylase enzyme that is involved in the metabolism of phenylalanine to tyrosine. So this deficiency results in tyrosine no longer being produced, and it's becoming an essential amino acid rather than non-essential. This deficiency is known as phenylketonuria and can also relate to deficiencies in BH4, which is a required cofactor for this metabolic process to be occurring. So tyrosine will need to be taken up as an amino acid supplement since it has become essential due to not being produced. And with that, that will conclude my answers for the Unit 4 Case Connections assignment.